Good, how are you?
Good. Don't get a lot of tutoring on Friday afternoon. Most people can't stand the thought, but what would you like to work on today?
I have a test on Monday that I figured we could do the review packet.
Okay.
And the first question is about a unit circle.
Okay. Go ahead.
And it has the angles 90, 60, 45, 30, and 0, and we have to convert the angles into radians and then write the location of a point if it were on a graph.
Okay. So let's take the 30. Let's start with the 30 instead of the 0. We can go back and do the 0 afterwards. Now, since it's a unit circle, that's 1, always. In other words, the unit circle is your first real exposure to polar coordinates.
Yeah.
Now, if I drop a vertical right there, then I could say, let's make that y, and this make that x. Then I would be able to say that the sine of 30 degrees is equal to y over 1, and the cosine of 30 degrees is equal to x over 1, or let's just take away the 1. In other words, the x-coordinate is the cosine of that angle, the y-coordinate is the sine of that angle.
Yeah.
Now, to figure out what those are, there's two triangles that are really, really useful here. You've been working with them since algebra, probably. And they're the 30-60 and the 45-45.
Yeah.
Now, I call these the unit special triangles, like the unit circle. And the reason, that's my name I made up for them, but the reason I did is because opposite the smallest angle is 1, which makes that square root of 3 and that 2. This is 1, 1, square root of 2. So, these are two triangles you want to be able to create from memory. They are going to prove invaluable to you when it goes to memorizing the unit circle. Notice that I can tell that the sine of 30 degrees is 1/2 from this triangle, and that the cosine of 30 degrees is square root of 3 over 2, and that the tangent of 30 degrees is 1 over root 3 or root 3 over 3.
Yeah.
Okay, so these two triangles allow me to compute the trig function of any of these first quadrant angles. In other words, there's also the 45, the 60, and they said the 0 and the 90. Well, that's 90, and that's 0. Now, notice that the cosine of the angle is always x. So this point right here is what? What are the coordinates on that point?
That would be 0, 1.
The cosine of 90 degrees is the x, the cosine of 0 degrees is 1. Because this coordinate is 1 comma 0. That's where I should have started. Okay? So if we wanted the cosine of 0, we can see that it's got to be 1. And the sine of 0's got to be 0. So that's the way you do the quadrangles. These multiples of 90 are called quadrangles.
Yeah.
And they're 180 over here, 270 there, and back to 360. So to figure out the trig functions of the smaller angles, we can refer to those two triangles right there. Okay? That also gives us the coordinates of each of these points, and that's what they want, right?
Yeah.
Okay. So what are the coordinates going to be of that right there?
Root 3 over 2 and 1 over 2.
And the coordinates of the 45-degree angle?
Root 2 over 2 and root 2 over 2.
The 60-degree angle?
1 over 2 and root 3 over 2.
Well, I think you got these down pretty good. And the 90-degree angle, since we can see that the coordinates are 0, comma 1, that's what they should be, right?
Yeah.
Because the cosine of 90 degrees is 0 based on this. Yeah. In other words, for these quadrangles, it's easier to read the coordinates and figure out what the two main trig functions should be. In other words, this coordinate over here is minus 1 comma 0. This coordinate down here is 0 comma minus 1. So based on that, what is the cosine of 270?
Cosine of 270 would be
it's this x coordinate.
0.
Yeah. What's the sine of 270?
Negative 1.
Correct. So if you know this unit circle and you know that these 4 quarter points here, then that allows you to figure out what the sine of each of the quadrangles are and the cosine of each of the quadrangles.
Yeah.
Of course, the other way is to memorize the curve, which you also want to do. Here's the cosine. This is the sine curve, and it's 4 quarter points. 2 pi, 3 pi over 2, pi, pi over 2, and 0. Goes up to 1, goes down to negative 1. Notice that I could also figure out the sine and cosine from knowing the curve. Here I'll draw the cosine over here. Cosine starts at 1. They each go to 2 pi after completing one cycle, and they each go bounce between 1 and minus 1, never bigger. In other words, if somebody says the sine of an angle is 1.2, it's impossible. The sine of any angle can only be, the maximum is 1, the minimum is minus 1.
Yeah.
Okay, converting to radians. It's pretty easy. The conversion factor when you have degrees is pi over 180. In other words, if I'm trying to convert 90 degrees, I'm going to multiply it by that. Why? Because I want to lose the degrees. And as long as the degree part is in the denominator, well then those will cancel and you'll end up with pi over 2 radians. Even though we don't tend to write radians. Once you get it into radians, it's unitless.
Yeah.
Which is another question altogether that we'll talk about at a different time. Radians and degrees are not the same as meters and feet or gallons and liters. It's not just a straight conversion factor, and now one is equal to the other. There's a very, very fundamental difference between radians and degrees. You can't do calculus in degrees. You can only do calculus in radians. It doesn't work if you do it in degrees. Radians are actually numbers, whereas degrees are degrees, a piece of a 360-degree circle.
Yeah.
But that's all we need to say about them for now. However, you can do this conversion for every angle, but what is pretty cool is that pi over 6 equals 30 degrees. Notice 30 times 6 is 180. Pi over 3 equals 60 degrees. Again, 60 times 3 is 180. Pi over 4 is 45 degrees. So this is kind of a convenient way of memorizing your first quadrant, 30, 45, and 60.
Yeah.
So does that cover everything you need to know, or do we just need to stay in the first quadrant, or do we need to go second quadrant also?
No, it was just the first quadrant.
Okay. Second
That
quadrant would be done exactly the same way. In other words, the x-coordinate is going to be the cosine of that angle. So if I drew my angle like that, which is a 120-degree angle, well, the x-coordinate is still the cosine of 120. Well, if you looked up the cosine of 120, it's the same as the cosine of 60, which is root 3 over 2, only it's negative. So that's going to be negative root 3 over 2. The y-coordinate is still positive. And
Yeah.
the y-coordinate is, cosine of 60 is actually 1/2. Excuse me, I got those backwards. So it's minus 1/2 root 3 over 2 for that 120-degree angle. And you could proceed through the whole unit circle that way. And they're going to ask you to memorize the unit circle. Okay?
Yeah.
That's what every school district in Colorado does, is ask you to memorize the unit circle. And there are 16 slices in that pie. There's 4 in each quadrant. And not only do they want you to know what the sign is of all 16 slices, but they want you to know all 6 trig functions of all 16 slices. So they want you to memorize 96 things. Now, that's quite a task to do. And there's easier ways to do it than memorizing a wheel. That's the hard way to do it. In fact, this whole little exercise we're doing here, to me, is the hard way to learn trig.
Yeah.
There is a formula that applies in the second quadrant and the third quadrant and the fourth quadrant. Have you seen these before?
No.
This is quadrant 1, quadrant 2, quadrant 3, quadrant 4. What these do, these formulas here, is allow you to take any angle greater than 90 degrees and convert it to a first quadrant angle. And the beauty of that is that means the only thing you have to really memorize are the first quadrant angles. And you don't actually have to memorize those, because if you can memorize these 2 triangles, you can figure out all of the first quadrant trig functions.
Yeah.
Okay? Now, what's the beauty of that? Well, I have to memorize 3 things there, and that's 1, root 3, and 2. Here, I have to memorize 3 things. 1, 1, root 2. Here, I have to memorize 3 things. 180 minus theta, theta minus 180, 360 minus theta. And finally, all students take calculus. What that means is that all 6 trig functions are positive in the first quadrant. Sine is the only positive one in the second, tangent in the third, cosine in the fourth. So if I present you with a problem of what is the cosine of 120 degrees, first realize that you're in the second quadrant, which means that's theta. I'm going to have 180 minus theta. So it's going to be the same numerical value as the cosine of 60 degrees. Well, I've got, what's that?
Wouldn't it be the same as negative cosine?
Yeah, I do it in steps. In other words, the first thing I do is find the numerical value, and the last thing I do is to put a plus or minus sign on it. In other words, the first step is to translate. This is the way I do it, and the way I think is the best way to do it. They may be trying to teach you other methods, but to me, memorizing a bunch of sets of 3 things is the way to go, as opposed to memorizing 6 things. If I gave you a 16-digit number to memorize it, you wouldn't memorize it as a 16-digit number. You would memorize it as maybe 4 groups of 4. Well, that's what I'm doing here, is I'm going to take every angle, if it's second, third, or fourth quadrant, I'm going to convert it to a first quadrant angle. Well, cosine of 60 is 1/2. Then I'm going to put the plus or minus sign on it. Well, I'm in the second quadrant because it's 120. Only sine is positive in the second, so cosine must be negative. Boom, I'm done. So the cosine of 120 degrees is negative 1/2. That's the process I use no matter what quadrant you're in. Basically, you end up relating everything to a first quadrant number and then attaching the sign based on these 4 things. All students take calculus. Notice that every single thing on this page is at most 4 things to memorize, including these graphs down here. The 4 things you need to memorize are these 4 quarter points. And these 4 quarter points are the same. That's pi. That's 3 pi over 2. That's pi over 2. And the quarter points are the key points of the graph. In other words, that's the pi over 2 is where sine hits its peak of 1, comes back through the x-intercept at pi, go down and hit its minimum at 3 pi over 2, and come back to its starting point at 2 pi.
Yeah.
So you could give me any angle, tangent of 225. In fact, let's do this. This is the way to teach trig. Might as well, there's no time like the present to do this. What would the tangent of 225 be?
It would be,
which quadrant, first of all?
it would be the third quadrant.
Okay.
And it would be positive.
Okay.
It would be the positive value of 45 degrees.
Okay, go up to this triangle up here and tell me what the tangent of 45 degrees is.
1?
That's plus 1 is what that's equal to.
Yeah.
And you can use that logic no matter what the angle or the trig function.
Yeah.
Positive or negative. Greater than 360 or not. If I said, what's the sine of 390? Well, I'm going to take out all multiples of 360, so that's the same as the sine of 30. From this triangle, that's 1/2. So now we can do any trig function for any angle as long as it's a multiple of 30, 45, 60, or 90.
Yeah.
This method that they're going to have you go through this whole unit circle doing this process for each multiple of those angles, that'll create the unit circle, but if you can memorize it, you're going to be a better person than I am. That, to me, is not the way to do it. I mean, it's nice to know that these points are created knowing that the cosine of the angle is x and the sine of the angle is y. That's a key thing to know for sure. But in terms of memorizing these points right here, I would rather memorize these two triangles, and they allow you to come up with those points. That's all you need is those two triangles. Now, when you get into the second quadrant, you need these. And in the radian there, the radian equivalent is pi minus theta, or theta minus pi, or 2 pi minus theta. So if you're dealing in radians, like what is the sine of 7 pi over 6? Well, which quadrant is that in?
It would be in...
This is pi here. This is pi over 2 here. This is 3 pi over 2 down here.
It would be in the third.
Okay. So I substitute 7 pi over 6 for theta. 7 pi over 6 minus pi. The equivalent first quadrant angle is pi over 6. That's 30 degrees. That's 1/2. So the sine of 7 pi over 6 is negative 1/2, excuse me. Because it's third quadrant sine is negative. Now, all students take calculus. That acronym is not quite accurate because really in the second quadrant it's sine and cosecant. And in the third quadrant it's tangent and cotangent. And in the fourth quadrant it's cosine and secant.
Yeah.
Because the reciprocal has to have the same sign as the trig function does.
Yeah.
But it doesn't make for a nice, pretty acronym if we do that. So we don't write that part. All right, what else? Let's see. I usually give pretty much the same lecture for Trig 101 unit circle to everybody. And I am so convinced of this is the correct way to learn trig that I usually end it by saying everything you see on this page you want to be able to recreate from memory.
Yeah.
Except this part here. The part that I don't really like their method of teaching. I mean, it's valuable to do that in the first quadrant, but to do that all the way around it is confusing and not particularly helpful, I don't think.
Yeah.
If you memorize the sine curve and the cosine curve, you don't even have to figure out these, you don't really have to know that the cosine of the angle is x and the sine of the angle is y. You could completely eliminate that information and it wouldn't hurt you in terms of figuring out all your trig angles. The goal here is they're going to hit you with questions like I did. Well, what's the sine of 300? Well, that's a multiple of 30. So I got to be able to do that by hand. And you can now do that based on everything you see on this page.
Yeah.
All right. What else are you covering right now besides that first exercise?
Well, the next couple of questions are choose one alternative that best completes the statement and give the exact value of tangent of pi over 3.
Okay. What angle is that?
60.
Yeah. And when you first start working with radians, most people will convert it. After a while, you get so you can almost think in terms of radians, and you don't have to go back and forth between degrees. Now, what's the tangent of 60 degrees based on this triangle right here?
It would be root 3 over 2 over 2.
It would just be opposite over adjacent. Opposite is root 3. Over adjacent is 1.
Okay.
So the tangent of 60 is root 3.
Yeah.
What were you going to say?
We do it where the hypotenuse is always like 1.
So that the what?
So the hypotenuse is always 1.
Ah.
So then it's like
Ah.
3 over 2.
Wow, that is different. I have seen school districts change this one so that it's root 2. They probably do this with you too. This triangle becomes root 2, and 2. And the reason they do that is it tends to rationalize itself. In other words, if I'm finding the sine of 45, it becomes root 2 over 2 instead of 1 over root 2, which then has to be rationalized. Now, for them to do that on this triangle, okay, I see the logic there, yeah. If you make that 1, then this becomes 1/2 and root 3 over 2. But notice now when you do tangent of 60, it's harder.
Yeah.
Whereas with my labeling, tangent of 60 is very straightforward. It's root 3 over 1. But it doesn't matter. These are the ratios are what count.
Yeah.
You can label these things with anything you want. Not sure why they make the hypotenuse 1 as opposed to 2. I see why they want to make this hypotenuse 2 as opposed to root 2, although not really. Even that doesn't make a lot of sense because there's 6 trig functions. In other words, this may make the sine of 45 degrees rationalized, but if you were to take the secant of 45 degrees, now you have 2 over root 2. And that has to be rationalized back to 1 over, or root 2 over 1.
Yeah.
So you give up something and you gain something by doing it this way. I don't like their 30/60 at all. I much prefer 1, root 3, 2. Why bring fractions into it? I don't see any reason whatsoever to have the fractions. It doesn't affect the rational number. Notice that if I have those numbers, everything comes out ready-made, done. When you divide everything by 2, in order to make this 1, it just kind of complicates it.
Yeah.
And there's no need to have that 1. It's not really related to the unit circle at all.
Yeah.
But that's not a big thing. I mean, whatever they do, I don't have any problem with doing that. It's the ratios that matter. Okay, what else?
Then there's cosecant of 60.
Okay. That is the same as 1 over the sine of 60.
Yeah.
What's the sine of 60?
Sine of 60 is opposite over hypotenuse, which is, for me, root 3 over 2 over 1. So
Okay. So root 3 over 2.
Yeah.
So this is 1 over root 3 over 2, which you have to flip. Now becomes 2 over root 3, which you then have to rationalize. And it becomes 2 root 3 over 3. Hold on a moment. In my scenario, whoops, the cosecant of this angle, okay, would be 2 over root 3, and you rationalize that. Okay, yeah. For some reason this didn't sound right. I guess I've never memorized my reciprocal ones. That didn't look like a common one. Okay, what else?
Secant pi over 4. So secant of 40 degrees.
Okay, secant is, the reciprocals are really important to get those memorized as quickly as possible.
Yeah, but 45 is pretty easy.
It is, but it's still 1 over what?
Root 2 over 2.
Okay. Which means
it's 2 root 2. So it's going to be
root 2.
Root 2.
Which you get directly if you do mine. Mine is 1 root 2. Notice that when you're working with secants and cosecants, this makes much more sense than root 2, 2. There's no rationalizing that needs done. When I want the cosecant of 45 degrees, it's root 2 over 1, as opposed to going through the 3 steps we had to. So sometimes rationalizing before you get done is counterproductive. In other words, I would have been better off, rather than writing that root 2 over 2, I would have actually been better off writing that 1 over root 2. Then you don't have to go through another rationalization. When you flip, it just becomes root 2 in the top.
Yeah.
So I guess the moral, what I'm trying to say is that don't rationalize early. Wait until you get done with the problem to rationalize. Because if you rationalize too early, you may end up having to rationalize again, not unnecessarily a second time.
Yeah.
Okay, what else you got?
Secant of 30 degrees.
Okay, so that's 1 over what?
That's
Let me give you a good way to memorize. Let's go through the reciprocals are so important. Let me give you a really excellent way to memorize. Here's your 3 main trig functions. Okay.
Yeah.
I know the other 3 are secant, cosecant, and cotangent. And each of them are the reciprocals of one of these. Well, the one that makes the most sense is obviously that one. Which means the only thing you have to do is be able to match up the secant and cosecant with sine and cosine. Well, that goes there and this goes here because every one of these reciprocal relationships has exactly one co in it. There's the co there, there's the co there, there's the co there. So you'll never end up putting cosecant with cosine.
Yeah.
And once you get that little trick, now you're set. You're never going to miss a reciprocal relationship. And these are definitely 6 of the most important things you're going to have to memorize in trig. You're going to get to verifying trig identities, and it's all about knowing these really well. Okay. And, of course, it works vice versa. In other words, cosecant is work 1 over sine. So you end up with 6 of them. So there's the 6 reciprocal identities. Now, the way I generally work with these is I like to work with, you know, your older calculators only had sine, cosine, and tangent on them. If you wanted to come up with cosecant, you had to do the sine and then do the reciprocal of it.
Yeah.
Kind of the way we're doing it now, and that's one of the reasons we're doing it this way, is that's the way I'm used to doing it, is working entirely in sine, cosine, and tangent, and just reciprocating where necessary.
Yeah.
What else you got?
Oh. Mm, find the 6 trig functions where sine of theta equals 2 over 3.
This is almost the classical trig problem. They give you the value of one trig function, and usually they tell you which quadrant it's in, and then they want all 6 trig functions of that angle.
Yeah.
And the solution is always exactly the same, and it doesn't matter that we're stuck in the first quadrant for now. You haven't gotten to the second, third, and fourth quadrant yet. Doesn't matter, the solution's always going to be the same. Draw a right triangle, label theta, and now dimension it as much as you can. Which sides can I dimension?
Hypotenuse and opposite.
Okay,
So,
the opposite has to be 2 and 3, and now using the Pythagorean theorem I can figure out this side.
yeah.
What's that side?
It's going to be square root of 13.
5. Let's talk about solving right triangles, because this is something you're going to have to do a lot of. And so you want to be able to do it quickly. You don't want to have to go back to the Pythagorean theorem every time.
Yeah.
If I am solving for one of the legs, the answer is always, in fact, it doesn't matter whether I'm solving for one of the legs or the hypotenuse. The answer always starts out square root of. So
Yeah.
if you're not starting your answer out with square root of, you're making a mistake. Now, if I put a perfect square in there, okay, then the answer is 4, but you can never go wrong by starting your answer out square root of. If it's one of the legs, then it's the hypotenuse squared minus the other side squared.
Oh, yeah, I added them, not.
Okay? If it's the hypotenuse that you're solving for, it still starts out square root of, but now it's the x squared plus, in other words, it's the other two sides squared and added together.
Yeah.
So that's the only difference, and those are the only 2 scenarios. So it's worth memorizing them directly. In other words, I understand that you can always start from this starting spot and come up with how to calculate C, how to calculate B, how to calculate A. But that's a lot of math to have to go through.
Yeah.
Given that the problem is always you're going to be solving for one of the legs of a right triangle, then it's pretty useful to be able to go immediately to this. Okay, and that's why I knew immediately it was square root of 5. Now, once you have this thing fully dimensioned, now all 6 trig functions are a piece of cake. What's cosine of theta?
Cosine of theta is square root of 5 over 3.
What's tangent of theta?
It's 2 over square root of 5.
Okay, which rationalizes to 2 root 5 over 5. What's cotangent of theta?
It's square root of 5 over 2.
Good. In other words, without having to flip that and re-rationalize, go back to your triangle, and well, it's got to be this side over that side. It's fully rationalized. about the secant of theta?
Secant of theta is 3 root 5 over 5.
Okay. And finally, the cosecant of theta.
It would be 3 over 2.
Now, these problems, once you discover the second, third, and fourth quadrant, these problems always come with a theta is in the second quadrant. Or they'll say theta is greater than pi over 2 and less than pi, which places it in the second quadrant. Okay? Now, the only difference in solving this problem as opposed to the one you gave me was the one you gave me, they were all in the first quadrant, so I didn't have to worry about the signs on any of these answers. But if I said theta was here, I would still draw this triangle like this.
Yeah.
Okay? And this triangle, and doing everything exactly the same, comes up with all 6 of the same numbers. Only now I know, well, I'm in the second quadrant, cosine's negative, tangent's negative, cotangent's negative, secant is negative, cosecant's the only one that's positive.
Yeah.
So adding the quadrant that you're in doesn't particularly make it harder as long as you can remember all students take calculus.
Yeah.
And that's why my entire approach to trig is to base everything off of first quadrant angles. Screw that memorizing the entire unit circle by, sticking it in your memory. I just do not think that's the way to go. For one thing, humans don't memorize stuff like that very well.
Yeah.
Okay, what else you got?
All right. Cosecant negative 1. This is nothing.
Have you gotten to inverse trig functions yet? Probably not.
I don't know what this is. It said cosecant negative 1.
Ah, you're looking at this. Right?
Maybe. I don't know. The way it's
called the arc. Let's talk about inverse functions.
Yeah.
Start with the simple ones. The sine of 30 degrees is equal to 1/2 if and only if the inverse sine of 1/2 is equal to 30 degrees.
Yeah.
Now, important concept here is we take trig functions of angles and we get numbers. When you take inverse trig functions, you're taking inverse trig functions of numbers in order to come up with the angle. In other words, if I give you a triangle and I say that's 1 and that's 2, what is theta? Well, you may know that theta is 30 degrees, but let's pretend you didn't. Well, you could say, well, let's find, hold on, let's find what the inverse sine of 1/2 is. And you can put that into your calculator, and it'll say either 30 degrees or pi over 6, depending on whether you're in radians or degrees.
Yeah.
So that's the key distinction. You take inverse trig functions of numbers to get angles. Because they may give you a triangle and say, figure out theta. And it may not be nice numbers. It may be numbers like that. So now the only way to solve for theta here is to actually go into your calculator and look up the inverse sine of 1/3. And inverse sine is the same as arc sine. There's 2 different methods of speaking about it. One, you can put ARC in front of it. The other, you can put this -1 exponent. which doesn't really mean negative 1 exponent.
Yeah.
Okay? It's not the same as x to the minus 1. X to the minus 1 is 1 over x. Sine of to the minus 1 is not 1 over sine. That would make it the cosecant. Inverse sine very clearly has a very specific meaning and definition. It is the sine of what angle is equal to 1/2, essentially. So back to your problem now. What was it? The cosecant and the inverse cosecant?
Of 1.26 to the nearest minute.
Okay. Got to go in your calculator to do that. I think I can do it on Wolfram Alpha. Yeah, let's see if it likes this terminology. Yeah, the arc cosecant of, what was the number, 1.26?
Yeah.
Okay. Gave me the result is in radians and degrees, and you'll notice that it's 52.53 degrees. So how do we change that to minutes?
Would you divide 360 by 52? No.
30,
Divide 52 by 360.
by 60. In other words, there are 60 minutes in a degree, and there are 60 seconds in a minute. Okay?
Yeah.
So when I write 52.53 degrees, I can say, well, that's 52 degrees and 53 hundredths times 60 minutes per degree.
Yeah.
So I have 0.53 degrees times 60 minutes per degree. You lose the degrees and you end up with minutes. That goes with that. What do we end up with here? 318, 1.8. Now, interestingly enough, is Wolfram Alpha didn't give me the result in degrees out to enough places such that I could round this off to the nearest degree or the nearest minute. In other words, because they only gave me 52.53, I couldn't get it any more accurate than 31.8. Oh, that does allow me to round it off. Yeah, that's 32 minutes. So the answer is 52 degrees, 32 minutes. Sorry, I got confused there for a moment. Minutes are, for some reason, they start out teaching you trig, teaching you about degrees, minutes, and seconds. And that's really the last time you ever hear about it.
Yeah.
Maybe with latitude and longitude you hear about it, but that's about it. Once you get past the latitude and longitude problems, you don't deal in degrees, minutes, and seconds anymore. You deal in these things. In other words, you deal in 52.53 degrees.
Yeah.
Okay, what else you got? It's interesting that they gave me the answer in radians to 6 places. But then on degrees, they don't even offer me the choice. Notice that I could have gotten the answer in radians to more digits. But they don't give me that choice on the degree answer.
Well, degree is like more accurate than a single radian, so maybe.
Well, not really. This is the more accurate of the two answers they gave me.
Yeah.
Just because it's out to 6 decimal places. Whereas this one is only out to 2 decimal places.
Yeah.
There was something beyond that 3, I'm quite sure. Unless it was 0. I mean, it could have been 0. I'd be surprised, but
All right.
okay, what else?
A builder has a ramp to its front doors to accommodate the handicap.
Okay.
The distance from the building to the end of the ramp is 14 feet. The height from the ground to the front of the doors is 8 feet. How long is the ramp?
There's the problem. Here's the house. Right?
So would we use the Pythagorean theorem?
You could actually use the Pythagorean theorem, but you could also use trig functions.
Yeah.
No, you can't. Excuse me. They didn't give you this angle. Well, we can figure out that angle. In other words, let's do it using trig functions. And I know you know how to do it using the Pythagorean theorem.
Yeah.
Square root of 8 squared plus 14 squared. Let's do it using trig theorem because I can figure out theta. I know the tangent of theta is 8 over 14, which means if I take the inverse tangent of both sides, I can figure out theta by taking the inverse tangent of 8 over 14. That's going to equal theta. Once I come up with theta, now I can say the sine of that angle, whatever it is 8 over the z, this being z, and I can solve for z because I'll know what theta is and that'll just be a number. So I can do it using trig functions. It's a little more laborious in this case, but still doable. But clearly the Pythagorean theorem is the quickest way to do it.
Yeah.
I'm kind of surprised they gave you the problem that was easier to solve with the Pythagorean theorem than it is by trig.
Yeah.
A better problem would have been not to give you the length of the ramp, but to give you that angle, 21 degrees. In other words, they give you that angle and they give you the height from the bottom to the house. Now you have to use trig functions to solve it.
Yeah.
Now you'd have to say the sine of 21 degrees equals 8 over z. So z would be 8 divided by this number that you get out of a calculator. That would have been a much better problem because it would have forced you to use your newfound knowledge of trig instead of your old found knowledge of the Pythagorean theorem. But
yeah.
So that's the square root of 8 squared plus 14 squared. Okay, what else?
All right, fill in the blanks with the trig functions cosecant theta, secant theta, tan theta, or blank. I don't know.
Okay.
And then the triangle is the hypotenuse is 5, and then the opposite side is 2.
So this is square root of 21.
Yeah.
Okay, and what do they want? They want you to fill in the blanks for those trig functions you were reading?
Yeah.
Okay, let's just do all 6 trig functions. And verbally, what's the sine of theta?
Sine of theta would be 2 over 5.
What's cosine of theta?
5 over square root of 21.
Sine and cosine are over the hypotenuse.
Root 21 over 5.
Tangent of theta.
That would be 2 over root 21.
Or
root 21 over 2.
don't forget that first 2. In other words, you had this. That always rationalizes. You end up with a 21 there and a 21 there, but you still have that 2.
Yeah.
So it's 2 root 21 over 21. Cotangent of theta.
It would be 2 over root 21. Or no, root 21 over 2.
Right. And that's why it's not always good to rationalize it. It's sometimes good to write it down just so when you have to do the cotangent, you can do it immediately. You know what I'm saying?
Yeah.
Okay.
Yeah.
And the secant of theta?
The secant would be 5 root 21 over 21.
Good. And the cosecant of theta?
It would be 5 over 2.
Uh-huh. You got it. Well, is that a good place to stop, or do you have any last questions that you are still puzzled?
I think I got it.
Yeah, I think you do too. Try to, I cannot stress this enough, try to memorize this page.
Yeah.
Not everything. Let's, hold on. Let me erase the stuff that's not important. Memorize everything you see on right there. There's no pieces of information on here that you don't need to know. Every single thing you need to know. And this is just a good thing to you to be able to recreate from your mind. You don't want to have to constantly refer to this page. In other words, you could have this written down somewhere and you constantly go back to it, but the moment you get every aspect memorized, you'll be fabulous in Trig, at least at this point.
Yeah.
Okay?
All right.
All right, Lucas. I will talk to you back on next Wednesday?
Yeah, unless something comes up.
Yeah, that's fine. I don't have any problem with that. Otherwise, I'll see you Wednesday at 3.
All right.
All right, bye-bye.
Bye.